All right, so as I mentioned, the midterm exam is going to be from these two modules. You don't have to go back. It's just about Module 7 and Module 8. And I'm going to start with Module 8, and then we go back to Module 7, so you can ask your questions about different parts of Module 8. So this is the last thing we talked about last session, cache performance. And we have some examples of the cache performance, as you can see here. This module is actually one of the modules that you have a lot of examples. So if you go back and read the slides, review the slides, you can see that we already have a lot of different types of questions. As always, if you want to have more questions, go and check the books, right? So in the midterm exam 1, I'm not sure how many of you actually checked the questions in the book, but that question was directly coming from the load word question, instruction enhancement. Without any changes, it was coming from the book. So you can take a look at the questions there to have more sample questions for the midterm exam if you want to. I'm not saying that for this midterm exam, I'm going to choose another one exactly from the book, but it's always good to have some samples there. So this module is one of the modules that we already have a lot of questions in it. So there are different variations of the questions, and you can also design questions for yourself. It's a very good practice that, if you're studying a team, one of you design a question, the other one answers it, and vice versa. This is something that can really help, because when you put yourself in the designer shoes, you learn better and try to find the corner cases. We covered everything in the class, obviously, but there are things that can be changed when we are asking the question, so we can be a little bit smarter about how this question can be asked, so that you're not confused. Because the exam is open book and open notes, you don't have to memorize anything. You just have to be ready for all possible scenarios in the midterm exam. You have 1 hour, 15 minutes. We're not going to have more than 4 questions in this midterm exam, and so you just need. You need your time, so you don't want to be surprised. You want to figure out what the question is asking in the first 2-3 minutes, and then spend the rest of it answering the questions, go to the right place in the module. You have to know where everything is. So know your material, even if you don't memorize it, know where it is, so you can easily open that slide and answer the question. So we're gonna have 2 sample questions here today on the Module 8, and I'm mainly going to answer those questions because you don't have a quiz on this module. So if I wanted to have a quiz, I would have given you these questions. Okay, so this could be your quiz, but now I'm going to solve it for you. You can ask the questions you have. So cache performance, we talked about different layers of the cache and so on, but we finished this part with the concept of AMAT, or average memory access time. So average memory access time is a metric that is used to basically find how much time it takes for each layer in the memory hierarchy to bring the data in. Okay, so this metric includes both the time for a hit as well as miss rate and miss penalty. So some of the examples that we had earlier before this slide, they were not considering the hit time. They were assuming that it doesn't take any time for us to go and break the data from the cache if the data already exists in the cache. That's not always the case. There is some time that needs to be consumed, even if there is a hit. Right? So AMAT is going to include that hit rate inside the equation. So as I mentioned, something that we have to be always very careful about are the units. So AMAT can be in seconds or it can be in clocks, right? So if you want to just make sure that you are consistent throughout the solution. If you're working with clocks, make sure that you're working with clocks. If you're making with time, make sure that everything you're using is already in time, okay? In seconds. Very important thing is that AMAT in cache layer n is equal to the miss penalty in cache layer n-1. So if I want to know what the miss penalty in layer 1 is, I have to calculate the AMAT in layer 2. And it just makes sense. Average memory access time in layer 2 is equal to the miss penalty of layer 1. Why? Because if you have a miss in layer 1, we have to go to layer 2 and break the data. Average memory access time of layer 2 is the miss penalty of layer 1. Does this make sense? Don't have to memorize this. It's just based on the definition. To me, this is clear. You miss something in layer 1, the average memory access time of the layer after that is equal to the miss penalty of the layer. Okay. So now with this information, we have this simple example, and we already solved this example. This is not very complicated. It has one layer of the cache. I just go over it quickly one more time. We assume that the processor has a 1 nanosecond clock cycle time and a miss penalty of 20 clock cycles, a miss rate of 0.05 misses per instruction, and a cache access time of 1 clock cycle. So this is an example of having seconds and cycles kind of mixed, right? So now we want to calculate AMAT for this one. So AMAT is equal to time per hit plus miss rate multiplied by miss penalty. Okay, so miss rate we already know is 0.05. Miss penalty is already mentioned here, 20 clock cycles, and the time for a hit is 1 clock cycles or 1 nanoseconds. So we can solve this in terms of seconds or nanoseconds by converting everything to time. So time for a hit is 1 nanosecond, miss penalty is 20 nanoseconds, right? And then we can have an AMAT of 2 nanoseconds or 2 clock cycles. Okay, so this is how we calculate AMAT if you have all that information. So now, the sample question that I have here is actually the PhD qualifying exam question 3 years ago. 2 years ago. Okay, so, and you can see that it's not really that difficult to solve, okay? But now let's see what it is. So we have a processor with a base CPI of 2 and a clock rate of 2 gigahertz that has a 2-level cache with the following information. So L1 hit time is 0. L1I, so this is the instruction cache, miss rate is 4%. L1D, which means it's a data cache, miss rate is 2%. Also know what these terms are, because I can ask the same exact question, just say L1I, it means that it's the first layer instruction cache. L1D is the first layer data cache. We don't have instruction and data caches after the first layer. Only in the first layer we have instruction cache and data cache. The next layer we just have a cache, a uniform cache. Okay? So the second layer of the cache has a hit time of 5 nanoseconds and a miss rate of 2%, and L2 miss penalty of 100 nanoseconds. So how can I change? I can have the same question with different words. I could have said the main memory access time is 100 nanoseconds. Okay? You should know that the main memory access time for the L2 cache is equal to the L2 miss penalty. So you have 2 layers of cache. Layer 1, layer 2 at memory. So I can either give you the information in form of the L2 miss penalty or the memory access time, the main memory access time. The main memory access time is equal to the last layer miss penalty. Okay? This is the same story as AMAT. It's always how long it takes for us to access the next layer of the cache. This is the miss penalty of the layer before that. Okay? So I could have said what the main memory access time is equal to 100 nanosecond here. It would have been the same thing. L2 miss penalty is 100 nanoseconds. Right? So now let's go back to the question. Assuming CPU is running a program with 20% load and store instructions, what is the effective CPI? Okay. So effective CPI. Effective CPI, we had this relation for this one last session, which is equal to the base CPI plus memory install cycles per instruction. Okay. Now, what is the memory install cycle per instruction? It's the AMAT of instruction plus AMAT of data cache. So if we calculate the average memory access time of the instruction and add it with the average memory access time of data cache, we will find the memory stall cycle per instruction, the average memory stall cycles. Okay? So now, AMAT instruction is equal to, this is the AMAT relation, we already know it, is equal to L1 hit time, instruction cache, plus L1I miss rate, this is the instruction cache again, multiplied by L1 miss penalty. AMAT data is going to be L1 hit time, both of these guys have the same hit time, right? Plus the load store ratio, because only for load and store instructions we go to the data memory. For every instruction we go to the instruction memory, but only for load and store instructions we go to the data memory. If we don't have load or store, we just use the ALU and we never go to the memory, so we don't even care about it. So that's why we have this ratio here. Load store ratio multiplied by L1D miss rate, that's the information that we have here, multiplied by L1 miss penalty. Okay, so now let's see what information we have here. We have the L1 hit time, good, it's already there. L1I miss rate is already here, perfect. Now we need L1 miss penalty. We don't have the information about L1 miss penalty. Let's keep it for now, and let's go to the AMAT data. For AMAT data, we have L1 hit time, load store ratio, which is equal to this part here, 20% load store instructions, so this ratio is 0.2. That's the information that's provided in the question. Then we have L1 miss rate, which is another, is provided here, L1D miss rate, 2%. And L1 miss penalty. Again, we don't have the information about L1 miss penalty. So how can we find L1 miss penalty?
Calculate the AMAT of the layer 2.
Exactly. So to find the L1 miss penalty, we have to calculate the average memory access time of layer 2. AMAT of layer 2. Okay, every time that we miss something in layer 1, it's going to take that much time or that many clocks to bring data from layer 2 to layer 1. So we have to calculate the AMAT of layer 2. The L1 miss penalty is equal to L2 AMAT. So now what is L2 AMAT? L2 AMAT follows this relation. L2 hit time plus L2 miss rate multiplied by L2 miss penalty. And that's the information that we have here. L2 hit time is 5 nanoseconds, L2 miss rate is 2%, L2 miss penalty is 100 nanoseconds. So this is the part. After this point, you know all the relations, you know, okay, you basically know how to solve this question. The thing that you should pay extra attention to at this point is making sure that these units are consistent. They're all in seconds or in clocks. Because I can ask a question in which I can say the L2 hit time or L2 hit clocks are 5 clocks. Or I can say L2 miss penalty is 200 clocks. And everything else is in seconds. Right? This is where a lot of students make mistakes. And that's basically because of you not considering other scenarios. If you try to design questions for you that just throw clocks here and there and seconds here and there, then you know that you have to pay attention to the units. So I'm emphasizing here, based on the experience that I had, both in grading the qualifying exams and comprehensive exams, and in previous classes, I know that a lot of students don't pay attention to the units. Okay, when it comes to the 100 nanoseconds, I emphasize on it here, and I still know that we're going to have at least 10-20% of students making mistakes. You know, so just pay attention. That's just tricky. It's not a big thing, but you have to pay attention to it. So now, for simplicity, everything is in seconds already here. So we go ahead with seconds, and we just convert it to clocks at the end. Why do we convert to the clocks? Because we care about the effective CPI. CPI is clock per instruction, it's not time per instructions. Right? So we basically care about clocks. Because we already have everything in seconds, we go ahead with seconds and then convert it to clocks at the end. Okay, now L2 hit time is 5 nanoseconds, and we have L2 miss rate of 2%, which is 0.02, multiplied by the miss penalty, L2 miss penalty, which is equal to the main memory access time of 100 nanoseconds. When I put 100 nanoseconds here, if you do the math, you get 7 nanoseconds. So we have a clock rate of 2 gigahertz. 2 gigahertz is equal to 0.5 nanoseconds. If you don't know how to do the conversion, make sure you practice it enough to do the conversion. Just divide 1 by 2 gigahertz and you get 0.5 nanoseconds. So if you divide 7 by 0.5 nanoseconds, you're going to get 14 clocks. Okay. So now I have the L2 AMAT, which is equal to 14 clocks. Okay. So now I want to find the AMAT of instruction and so on. So this is the part that it could, I think we intentionally tried to make it a little bit confusing so you can see the conversions. But if you don't convert it to clocks, you can continue with seconds when you go to the AMAT instruction and AMAT data. But if you convert it to clocks, you need to make sure that when you're calculating the AMAT instruction, everything is in form of clocks too. Okay, so what does it mean? We have AMAT instruction is L1 hit time. L1 hit time is 0. Then we have the L1 miss rate, L1I miss rate, which is 4% or 0.04, multiplied by 14 clocks here. So this was a qualifying exam question. If I wanted to design this question, I wouldn't put 0 here. I put 2 nanoseconds, and a lot of people would make mistakes. Because when you come to this part, you use the clock here, right? If I just put 1 nanosecond, a lot of people just forget to convert this 1 nanosecond to clocks. So you just put 1 here, and you go ahead with the clocks, and now you're mixing time and clock. So before going to AMAT instruction, if I had a hit time, right now I'm just designing new questions with you, right? That's the whole point of this class. That's how I designed the question. I sit one day at home, and I was just like, okay, let's add some hit time here and see what's gonna happen. Sure. So if we had 1 nanosecond here, then when you go to the AMAT instruction, you have to convert to 1 nanosecond to clocks, which would have been 2 clocks. This case happens to have the L1 hit time of 0, and even if you don't know that you have to do the conversion, don't make a mistake. That's an easy question this time. Okay, if you want to make it difficult, you have to add a little bit more complexity to it. So you're lucky. At this point, this is 0. You just multiply the 14 clocks by 0.04, which is the 4% here, and you get 0.56 clocks for AMAT instruction. For AMAT data, you have the L1 hit time, which is 0 seconds, plus load store ratio, which is 20% or 0.2, multiplied by L1D miss rate, which is 2% or 0.02, multiplied by L1 miss penalty, or L2 AMAT, which is 14 clocks. If you do the math, you get 0.056 clocks. Now, if you want to find the effective CPI, you have the base CPI plus AMAT instruction plus AMAT data. And you get 2.616 clocks. That's your effective CPI.
Yeah, I have a question. Why don't we consider the memory stall of layer 2?
Why don't we consider what?
The memory stall
Of layer 2.
of the layer 2.
So that's the thing. So if you only talk about layer 1, the memory stall of the layer 2 is the AMAT 2, L2 AMAT, right? So L2, if you just look at the first layer, to find the AMAT of first layer, you need to consider the memory stalls of the second layer, which is AMAT L2.
Oh, I got you.
Right? So the fact that we're using AMAT L2 and AMAT L3 and so on is bringing those stalls to the conversation already. Okay? So we always start with so the question was, why don't we consider LMAT or AMAT of layer 2 in this relation, this equation here? Right? Why don't we say AMAT data, AMAT instruction, AMAT layer 2? If you look at these equations, this is already included, the L1 miss penalty. If you had multiple layers, I'm designing another question right now. This is 2 layers, I give you 3 layers, right? So for this, you have to find L2 AMAT. But to find the L2 AMAT, you have to find the L3 AMAT. right? So because we keep using every layer, we bring them into the calculation anyways. So those stalls are brought to the calculation through L2 AMAT. Okay, any questions? Okay, so this question has a second part too. This is partial credit too. The second part is asking what is the overall speed up achieved from reducing the L2 miss rate by a factor of 2. Okay, so what's the speed up? This is the kind of question that I would like to ask from you in the final exam. Maybe in the midterm exam too, but like this is about speed up now. It's not just about calculating the effective CPI, it's about the speed up. Speed up was something that we covered in Module 2 in the quantitative analysis part. So it's like mixing two different modules together at the same time. So we're talking about speed up. We know here that the number of instructions is not changing and the clock frequency is not changing. Why it matters? Because when we want to calculate the speed up, we need to find the execution time of the CPU. When you want to find the execution time of the CPU, you have to calculate the instructions, multiply that by clocks per instruction, which is CPI, and multiply that by instruction time. The total number of instructions, multiplied by clock per instructions, multiplied by clock cycle time. Okay? So in this case, in this question, if you look at the frequency is not changing. It means that the clock cycle time is not changing. And we don't have any information about any changes in the instructions. So it means that the number of instructions is not changing either. This is again an easy question to design. If I wanted to design it especially for a qualifying exam, I would have definitely changed the clock frequency. Or something about instructions. Because when you go, you just assume that they calculate the CPI and compare the CPI good, but then you have to keep in mind that clock frequency matters too. This question, you're lucky because the clock frequency is not changing, the instructions are not changing. It means that we can just look at the CPI and compare the CPI of the old design and the CPI of the new design to get the speed up. And that would be enough. Okay, so let's do that. Let's just calculate the new CPI. So the new CPI, we have the same relation. Effective CPI is equal to the base CPI plus AMAT instruction plus AMAT data. AMAT instruction is equal to L1 hit time plus L1 miss rate multiplied by L2 AMAT, which is the miss penalty for the layer 1. Same as for layer 1. AMAT data, we just include the load store ratio. I'm repeating one more time. Because for every instruction, we go to the instruction memory, but only for load store instructions, we go to the data. Okay, but this is basically the same question. The only thing that has changed here is this L2 miss rate, which is reduced by a factor of 2. So we used to have the L2 miss rate of 2%, now we have the L2 miss rate of 1%. So we put it in the same equation, we do the calculation, this time we get 12 clocks instead of 14 clocks. This is AMAT L2. Now if you want to calculate the AMAT instruction using the same relation here, you get 0.48 clocks for AMAT instruction and 0.048 clocks for AMAT data. If you add them, this is what you get, 2.528. And what would be the speed up? But the question is not asking about the CPI. The question is asking about the speed up. So what is speed up here? We have to divide the CPI of the old design, because speed up has an inverse relation with the execution time. We have to divide the CPI of the old design by the CPI of the new design, and you get 1.035 speed up, or 3.5% improvement. Does that make sense? So now let's talk about the variations. Some of the variations we talked about, we can add L1 hit time, that can make things complicated. I can change the clock frequency, that can make things complicated. I can change the instructions, I can say, okay, the new design, we improve the frequency, we improve the cache, but the problem is that we're going to have, or we change the program. Let me make it a little bit more scientific. We use a different type of processor that has a different type of instruction set architecture, and for that, the same code, we need to run, when we run the same code, now we're going to have 35% load store instructions instead of 20% instructions. So now in the second phase, the ratio is changing, the hit time is changing, a lot of things can happen, right? A lot of potential for making mistakes. Not that I'm going to do it. If I wanted to practice for the exam, I would have practiced it that way. Okay? Let's make it as complicated as possible, and if I give you an easier question, good. You can solve it. Any questions about this? Go ahead.
Professor, can you have a question in which we also have L to D mystery?
Can we have what?
L to D mystery, data mystery.
L to D. So we don't separate the cache in the next layers. That said, you can design a memory hierarchy that has L2D and L2I. We don't usually do it. That's not a very common practice, right? Because both of them are connected to L2, to one, uniform cache that is supporting both L1D and L1I. As I said, that said, you don't have to have it that way. When you go to the next layer, you can also have separate, caches. Okay. And if you have separate caches, it means that you have a dedicated. I'm just trying to. It's as if you ask a question in the exam, I'm trying to solve it, right? So if I try to solve it in the exam, I would have said, okay, we have an L2D cache. It means that the L2D is dedicated to L1D. So if I want to calculate the AMAT, the AMAT L2D should be calculated separately, and LMAT L2I should be calculated separately, and then that's going to get, it's going to be used for L1D and L1I AMAT. Okay, you basically have more dedicated, caches. That's possible to do. Not a common practice though. Not many people do it in their processors. Any other questions? Perfect. So this is a good question that I can ask in the exam. I probably will. I'm probably going to have this kind of cache performance calculation, most probably. Another type of question that we can get is about bit field encoding. Okay, so we spent the first half of this module, we're talking about bit field encoding, right? How many bits we need based on the cache information, right? I most probably going to ask another question about bit field encoding too. Okay, so this is an example here. You can have different variations of this example. It is up to you to go and practice and have more questions like that. So this example is a MIPS-based tablet system that has 1 gigabyte. Hey, this is extra, I have to remove this. This already has 1 gigabyte of main memory and a 2 megabyte 4-way set associative mapped cache and a block size of 32 words. Okay. So I have this partial credits here, but probably I'm not going to ask it like this. I'm just going to ask about the bit field encoding. And you have to know what fields we need. So basically, because I'm not going to ask questions like this, for now I'm going to do it, but in the exam it's not going to be like that. You need to know the bit field encoding for each of the cache types. So you need to memorize it because you have the slides with you. So you see the set associative mapped cache, you go back and check the bit field encoding and see what field it has. Okay? Now based on the fields that it needs, you have to calculate how many bits you have in those fields. Right? So now let's start with this one. The first question is, how many bits, I do want you to participate in this one. Okay? So how many bits wide is the main memory address bus A, or the parameter A in the bit field encoding? So we have an answer for choice C. Anyone else? Who else thinks that C is the right answer? Allison, Blake. Yeah. Me. Christopher. Who else? Rahul. If not C, what else can be the answer? Who thinks A is the right answer? Who thinks B is the right answer? C, I already know. Who thinks D is the right answer? How about E? Okay, so we have some people that care about C and some people that don't care about the class, right? So let's calculate the number of bits. So we have how many bits wide is the main memory address bus A. So to find how many bits we have in the main memory address bus, we have to find the capacity of the main memory and keep in mind that the main memory is a byte addressable memory. So we want to have one address to every byte. So it means that we have to check how many bytes we have in the main memory. It's 1 gigabyte, 1 is 2 to the 30. So we have 2 to the 30 bytes in the main memory, which means we need 30 bits to address each of these bytes. So the right answer is C. So we go for 30. Okay. So how many bits wide is the byte field? We have the byte field. B.
Yeah.
Who else thinks B is the right answer? Xander thinks B is the right answer too. So how about E? Okay.
I have a question. So, generally, does it happen in real life? Say, we have two tablets. One is 1 GB memory, and another is say 4 GB memory. And do the hardware implementers really change the address bus in both of them, or say just attach different modules?
So that's a good question. Let's say we have two tablets. Really, we have real tablets, and one of them has 1 gigabyte of main memory, and another one has 4 gigabytes of the main memory. Do we, as designers, really change the size of the address bus because of the size of the main memory? Today, no. Like if I'm AMD, I wouldn't do it. Because you have already designed instructions and architecture for 32 bits. Just don't use some of the bits. Right? You just don't use the top two. I don't need those bits. Because it's hard to develop an IP. It's not because it's more efficient. It's because you don't want to recreate the IP over and over. Right? It's just easy. There's a protocol, it's designed, there's a standard for it, and you go for it. Yeah. So really, if we have smaller main memory size, we don't change the address bus. But right there's an opportunity for a startup company, right? I'm just oversimplifying things, right? So if I have a startup company, and if I want a corporation like AMD wouldn't change my IP or instructions and architecture for that. If I find a target, let's say I want to develop this kind of startup idea that I really like, and I might end up working on it someday, is that we develop some specific embedded systems for specific applications. So we have collaboration with a company, a robotics company. And this robotics company is telling me that I want to make fish. This is a real case scenario, by the way. This is a real collaboration. It's not just some imaginary scenario. They want to make facial expression recognition now. Why? Because in social robotics, they want to find out the facial expressions. So my lab, as an embedded system designer, just says, okay, you know what? I'm going to make it very efficient for you. I know AMD is not going to create a chip or not a board that has specific design for your need, and then I'm going to do it. Then I might design an address bus that has 14 lines, right? You can't really get a big company, but you can be a small startup to design specific architecture and boards for specific applications. Yes? Yeah. Did I answer the question?
Yeah.
So how many bits wide is the byte field? So what is the byte field? Because it's byte addressable, we want to address bytes in the word, right? So we have to know how many bytes we have in each word. So here you can't really see how many bytes we have in each word because we don't know the word size specifically, but it's implied by saying that it's a MIPS-based processor. A MIPS-based processor, it means that each word in MIPS has 32 bits or 4 bytes, which you're right. 4 is 2 to the 2, it means W is going to be equal to 2. Okay. Next one. How many bits wide is the word field? word field is used to address words in block or line of the cache. So block size, if you look at the block size, it has block size of 32 words. And it means that we have to put 5 words in each block. So it means that we need 5 bits to address each word in the block. That means that m is equal to 5. Okay. So how many bits wide is the line field? Line is for knowing how many, for addressing the lines in the cache. 21? Who thinks it's 8? Blake? You think it's 2?
Yeah.
So Blake thinks it's 21. You think it's 2. What else?
Doesn't matter.
Christopher thinking it doesn't matter. Why are you laughing? That's the correct answer. Yeah, it's not applicable, right? Because it's not a direct map cache. It's a set associated cache. We don't have address for lines, right? So that's true. That's correct. It doesn't matter. It's not applicable. It's a set associative cache. We do have flexibility within the set. We mentioned that when we have set associative cache, we have addresses for each set, right? But we don't address the lines specifically. We have flexibility within the set, right? So it's not applicable. We don't have a field of n, right? So next question. So now that we know that we have sets, we have a field called set in set associated. How many bits wide is the set field? So we have 2 here, which is choice B, right?
Yeah.
Xander thinks it's 2 as well. Mike thinks it's 2 as well. What does Matthew think? Matthew, what's the right answer? We have 1 Matthew there. Go ahead. Don't want to answer? Ian? Raul? Diego?
I think it's 2.
You don't think it's 2? You do think it's 2 as well. Okay. Raul, go ahead. Do you think it's 2 or not? C is the right answer, 5? Oh, C is like 4? Okay. So it's a little bit more complicated. Okay. So we have a set. Every line in the main memory is mapped to a set. So now we have to find how many sets we have in the cache, right? So it's a 4-way set associated map cache. If I find the capacity of every set, and if I divide the full capacity of the cache by the capacity of the set, I can find how many sets I have in the cache. It's a little bit more complicated. So that's the first thing we need to do, is finding the capacity of the set. We have a 4-way set associative map cache. It means that every set has 4 lines. Every set has 4 lines. Every line has 32 words, right? Because we know the block size is 32 words. And every word has 4 bytes. So 4 bytes is 2 to the 2. 32 words is 2 to the 5. It means that we have 2 to the 7 bytes per line, right? But we have 4 lines in each set. 4 is 2 to the 2. Multiplied by 2 to the 7 is going to give me 2 to the 9. So it means we have 2 to the 9 bytes in every set. So that's the size of the set. Then we have a cache size of 2 megabytes. 2 megabytes is 2 to the 21 bytes. Mega is 2 to the 20. We have 2. It means that we have 2 to the 21 bytes in the cache. And we have 2 to the 9 bytes in the set. So how many sets do I have now? I have to divide 2 to the 21, which is the size of the cache, by 2 to the 9, which is the size of the set, which gives me 2 to the 12. So it means that I need 12 lines to find this. Does this make sense? It's a little bit confusing, but not that much really. We just need to pay attention. The common mistake is that we think the set field is about how many lines we have in the set. But something that we need to remember is that the lines in the set, we don't even address them. They're flexible. That's the whole idea of set-associated cache. Right? In the set, we don't address the cache. Okay, we just have a tag field. We just randomly place, not randomly, we just place them in the whatever open spot we have in the set. So we don't need to address the lines of the set. But we need to address the set because every block in the main memory is mapped to a set. We have to find how many sets we need. That's how we can find how many sys we have. Does it make sense? So this was a set-associated map cache. What is the T? T is A minus S minus M plus W, which gives me 11. 30 minus 12 minus 5 minus 2 equal to 11. Whatever is left is tag. So now I can design a fully associative cache and ask you the same question. Right? So if you practice the same question for direct map, fully associative, and set associative, and maybe do it 2-3 times for set associative, because that's more complicated. Direct map is straightforward, fully associative is kind of straightforward, because it's actually easier, because it doesn't have a set field, it doesn't have an end field, so it's like pretty straightforward. You just get go M and W, and everything else is tag. Set associative is the one that is a little bit more complicated, and the one that makes it complicated, the field that makes it complicated is a set field. Okay, and we learned that through this example. None of us had a correct answer for set field. Right? It shows how complicated it can get. So that's bit fill encoding. So these are the types of questions you can get in the midterm exam, plus the other examples that I provided in the module. I just want to quickly go over module 7. So one type of the question is the question that we got in the quiz, but other types of the question that I would have focused on, if I were supposed to take the midterm exam, I would have just studied this a little bit more carefully, would be this question. It's pretty much like what you got in the final exam, in the project 2. Give you a code, lay your seeds, and you have to do register renaming, you have to optimize the code, you have to reorder instructions based on this latency, and find the maximum IPC, or the minimum CPI that it can get. Okay, I already removed that slide that was wrong, thanks to Regina. So you don't see it anymore, but this is the correct answer.
Would you give us the code in C or?
No, you don't have to do C to assembly conversion. It's going to be an assembly code. I give you an assembly code with the table like this. Usually when I don't provide the information in the table, it means that you either don't need it or it's zero. A good thing to do is, and it's the same thing for comprehensive exam, qualifying exam, and so on. If one of this information is not provided, assume something and go ahead with it. Solve the question, assuming that it's going to be zero, for example. But in many cases, when I don't provide the information, I'm giving you a hint. And that means that you don't even need that information. Right? You don't need to deal with that problem. So like there are many cases, obviously like in this table, and Regina, we had some back and forth in the past few days about this table and the exam, and you were right on one of them, I fixed that. But in some cases, it means that you don't really need that information. Okay? So you have to pay attention. For example, the cases that we have here are going to be covered by this table. If you think that you need this table, you need more information in the table, I might be wrong and I might provide that information, but also before that, think whether you need it or not. Like, for example, do you need to have information about, a lot of cases I haven't provided here. So, yes, it might be a hint. It might be not you not needing that information. Okay, so but this is a question in module 7 that let's make it easier. I'm definitely gonna give you a question from this. You're gonna get a question from this. Reordering and calculate the IPC. Okay? So, you have 25 minutes. I'm done here, and I can be here to answer your questions. Some of you might have questions that can be useful for the whole class, so maybe you want to go and ask it. But if you don't have any questions, feel free to leave. Go ahead.
Can I make a request? Are you going to upload your videos to your YouTube channel? The last like 4 lectures?
Yeah, we're gonna do it. He left, so I'm gonna ask him to do it as soon, like today. Yeah, so we have to crop it. We have to put it. Yeah, sure. And we'll do it today.
So I have a question about fully associated cache. As far as I understood, is that the hardware needs to look up through the cache to find specific address.
Yeah.
So in contrast to direct mapped cache, so what's the hardware that does this search, or is there like?
How do you find an address in it? So there are mechanisms to find an address within the cache, you know. So, but those are comparing bits and everything. So they are specific hardware. It's just any hardware that compares two numbers, right? So you just check a value and go to a specific location and the address bus find in the memory. You do have the row. So in the memory, if you have a row selector, you have row decoder and column decoder. These are the things I didn't talk about because it's a circuit kind of thing. So those decoders are responsible for finding the specific line in the cache. So all of these bit cells that I have in the cache, they have lines that select them. So we have bit line, source line, word line, and so on. So basically address goes to the decoder. And at the output, so the way it works is, so usually this is how we show the decoder, sorry. And we have like, for example, 8. We have 3 to 8, for example, decoder. We have 8 lines. Okay. The way that decoder works is that when you have an input, for example, 0, 1, 0, only this bit is going to be 1, and everything else will be 0. So when you have 0, 1, 0 as the input, only the second line will be activated, and everything else will be 0. So if you have an address of like 32 bits address, it's going to be a 32 to 2 to the 32 decoder. So only one of these lines is going to be activated at a time. These lines are the block slices that we can talk about. Like, you know, this is connected to the memory. We have different bit cells here and so on. So this is going to be, for example, the bit line. And this is going to, or the word line. This word line is going to activate this entire path. Then you have another decoder here that chooses, for example, the bits. And it says, okay, this byte is the byte that I care about. Okay, so you have a bunch of decoders all around the peripheral circuitry of the memory that is choosing from this. But the problem here is that this is such a huge decoder if you want to go to the main memory. So if you look at the transistors, the number of transistors that you can use in decoders are used with different switches, transmission gates, and so on. And if you look at how many transistors you need for example, a 32 by 2 to the 32 in a decoder of that type is thousands of transistors. So that's why breaking them to smaller pieces is going to be more efficient. Having this kind of hierarchical addressing is going to be better. Find the byte first and then find the forward first. So that's the whole idea. We don't want to have a huge circuitry handling all this, activating different parts of the line. But the whole concept of working with memory is about how you activate different lines of words, and it's going to find that location. We usually have sense amplifiers, for example, like you have a sense amplifier connected to this. You activate that word line, and it's like routing. It's a routing problem. These routes are connected. It's like a network. Everything is routed. Every cell is routed, and then you have switches, and you specifically select that specific location through that routing. Yeah.
So the search is basically the constant time. There is no penalty for, say, information is at the first of the cache or at the
Absolutely,
last.
there's penalty. So the question, that's a really good question, is that if I want to, let's say my decoder is placed here, and my cell is right here. So these are like high-level questions, but I'm answering them because we have time. So let's say there's a cell here, and there's a cell right here. If you want to access them, the cost is going to be different. There's a concept called, we recently had a paper, 2 papers on this topic. One paper in a conference and a journal which I accepted last year, is that these lines, it's very like, okay, I can explain a little bit about it, but these lines are, so when you transfer the information in a line, it means that the electron is going from one side to another side. So like basically this is the transfer of information. You have a bunch of electrons and you shoot them from one side to another side. That's the transfer of information. That's how Transistor Works memories. You're literally working with moving around electrons. Okay? So now when you have lines like this, if you don't know what capacitor is, capacitor has 2 kind of metals, and there's some kind of an insulator between them. So these lines can form a capacitor when you have lines of memory arrays. So what's going to happen is that you want to transfer electrons from here to here, but then they get trapped here in this insulator. Now no electrons go from one side to another side because they keep getting trapped at the capacitor. So what you need to do is you have to make sure that this capacitor is fully charged, and then you can transfer the information. The longer this path is, the more electrons are going to be trapped in this insulator, and the longer it's going to take to transfer this line from one side to another side. This information is called parasitic capacitance. So like these lines, they actually matter. Like this, but we always design it for the worst case. How do we fix this problem? We design it for the worst case. That's how many clocks it takes to read the data. So when I told you that when we have large sizes of memory, it's going to take more time to access data. This is one of the reasons. Besides having this large peripheral circuitry, the bigger the memory is, you always have to, the worst case that you want to design your system for gets worse. Right? But this is a lot of electrical engineering involved. We do research on that in my lab, but like this is not a computer architecture thing, it's a computer circuit in the research. Any other questions? Go ahead.
Can you go to slide 38?
13 up here
38.
in the memory hierarchy, right?
38.
38.
38. Okay. My bad. 38. This one, okay.
Where is the information here that it's byte addressable?
Where is the information that is byte accessible? You could, yeah, that's a good question. So how do we know it's byte accessible? Our assumption here in this class is that all the numbers are byte addressable. But I could have said like, half byte accessible, and that changes everything, right? I'm not gonna ask that question. Yeah, so it's like implied. Every question that you get here is byte accessible. The memories are byte accessible. Well, I could ask the question like that. I could. For this case, byte addressable is also word addressable, okay? For this specific hierarchy. But yeah, that's a good point. I could have, if I wanted to make it complicated, I said like it's half byte accessible or something. But no, it's implied. Yeah. It's not implied. It's an agreement that we have. So all the memories are byte addressable. Go ahead.
Can you go to other slide? Like
What's the number?
170.
47?
170.
Module 7.
Module 7. 51. Oh yeah, so this is this question, right? Why do we have 2 RT here, right? So I haven't thought about it. I don't think we need 2 RT. I don't know why they put 2 RTs here. That might be just something in the figure or something that I'm missing. But I don't think you need 2 RT here. You don't need 2 copies of that. Especially because both of them are RFID or register RT, don't need that. It might be a typo. Or I might be wrong. I don't mean why do you even need to have 2 copies here? Even if you want to have copies, you put it in the register. So maybe they are, actually you know what? I know why they're doing it. Because they use it here. So they want to make it faster. So they use 1 RT in this multiplexer and 1 RT in the forwarding. But another way of showing it was just connecting this RT directly to this one. So you see this is going here. Another way using it that way. Just ignore it. Just ignore it. Yeah, I don't think there's any reason to have 2 RT.
Can you go to slide 61?
61. Okay.
Now it's at slide 61.
Not 60. Oh, not this one. Yeah, so go ahead. I know what the question is. The question is how do we get 72 after 72 here? Right? So it's really what you need. There are 2 ways that you can show branches. One is I put the actual, this is the way that we learned it, this is the way that the book provided it. But if I wanted to do it, I would have said to put 7 here instead of 28. Because the way we fixed, because we did the branching was we got the branch offset, we multiplied that by 4, right? And then we got 28, and then we added 28 to PC plus 4 to go to the branch. That way you can get the PC, the target address, which is what it is. So we have 4, PC plus 4, which is 44, and then we add 28 to 44, we get 72. The thing that is causing the confusion is that when we talked about the encoding, we didn't put 728 here. We should have put 77 here, right? I think the right thing to put here is 7. This is directly coming from the book. But this came like 2-3 chapters after they talked about the encoding, so they didn't really worry about like how we show it here. It's like, okay, 28 plus PC plus 4 is 72, but in reality here it should be 7.
Are there going to be any questions where we have to draw on the exam? Like all the data pipelines?
Yeah. Like a question like, forwarding and everything, right?
Yeah.
You really wanted to narrow down the questions with that answer. And we might have give you a question.
Well, I mean, if they're like printed on the page and I don't have to draw them, that'd be easier. But
Absolutely,
I have to draw
yeah.
out all 5 of them.
And if we give you the answer, it's going to be much easier.
Yeah, but I mean,
No, I'm kidding.
I know what they look like
You
on
should
the
do a
slide.
little bit drawing, yeah. You might. I'm not saying I will, but we might have questions like this. That, you have to draw and find forwarding and so on. Any other questions? Tim, you want to talk? Do you want to answer?
My question was related to specifically my project,
Okay.
so I don't think it's a general question.
Sure, we can talk. Alice,
Are we gonna have something like I think it was quiz 7, where we ended up taking it home, where you draw like another part of the forwarding unit?
no.
Okay.
The question was, do I give you something like the homework assignment that you had to take home and draw something? I'm not going to give a question like that because that needs more time. You can't answer that within 1 hour and 15 minutes. You need more time to focus on it. So no.
And you said it was gonna be 4 questions?
It's going to be 4 questions, but some of the questions might have partial credit. But I make sure that you can answer all the questions. questions in the 75 minutes that we have in the class.